So we're going to talk about sign distance functions, or as some people erroneously refer to it as sign distance fields. Those people, including myself, quite often. If you already know what this is, skip this chapter. You will learn nothing new from it. If you don't know, let's talk about it. Basically, they are voxel grids. They are, volumes essentially. We're used to volumes. A lot of times they store density, just a number from 0 to 1 or higher that just says how much density there is in a particular voxel. And that's cool. Um, Sign distance functions, though, also known as distance VDBs in the parlance of VDB, but it's the same exact thing, is simply another voxel grid, but instead of storing densities to denote where something is as like a thick thing, this is storing in every voxel how far we are to the nearest surface, or at least where the surface was here when we turned it into a volume. Now, what we see here in the viewport is the surface. So when we are a distance of 0 from the surface, which is the value that's going to be stored in those voxels, that's how we know to draw the surface here. But really, it's a full voxel grid is. Or is it? We have in Houdini two kinds of volumes. There are basically Houdini volumes that just say volumes, and there are VDBs, which are also volumes, but they try to take a more memory efficient approach. What that ends up looking like is a kind of a wacky looking voxel grid that is trying to store information only where it's necessary. Another way to look at it is this VDB visualized tree, like so. Still kind of wacky, but essentially we are trying to only store those values near the surface. So we have this idea here of exterior band voxels and interior band voxels. That basically means that when we slice up this space into voxels, we know where the surface is right now when we make this. So only store how far we are, the values in those voxels, only store them 3 voxels, up to 3 voxels away, and then including to the surface, and then up to 3 voxels on the inside. So you end up with a band that, again, goes from 3 out to 3 in, so like a 6 voxel band that goes all the way around the head, and only in that area is the actual data stored. The idea being that that is enough to capture where the surface of this is, because we only really care about where it's 0, and then maybe a little bit on each side. No point of storing the distance to the head all the way out here. And yet sometimes there is a purpose. A lot of times in simulations we do always need to know. So that's why both things exist. This is less memory efficient, but actually stores the information everywhere, and is also, I think, slightly faster to look up the result into, technically speaking. That may not be true, so don't hold me to that. And then this side, which is VDB, which again is the more memory efficient thing. Now, to really fully visualize, literally, what we're talking about, here we are. I have a switch here where the VDB version is coming in on the left side. So you can see out here, it's red. All these are the values greater than 0, and then at 0, it shows white, and then blue when the values are less than 0. So we have a pretty good representation of the pig head here. You can see, obviously, when we move it around, it updates this grid. I have those values being copied from the volume onto the grid here. I'm storing it as a variable I call phi. Now, like I said, we are currently only storing those values up to 3 voxels away. And the voxels, if we look at this, are 0.1. So the furthest possible voxel from the surface is 3 voxels times 0.1. So the highest number in here is 0.3. And we could prove that to ourselves by looking at the phi values. 0.3 is the highest value, and they go down to negative 0.3 on the inside. Now there are, of course, distances out here that are clearly higher than or farther away than 0.3, but they also just think that they are 0.3 because the VDB only stored information here. Everyone else out here has to simply just look at where the closest, they find the closest voxel to themselves, and they just say, I'm that too. So that's cool in terms of memory efficiency, and that matters quite a bit, quite often. If I were to switch this to the other one, you can see now it looks different. And that's because on this one, there really is no limit on that. The phi's go all the way up and they go all the way down. This is a dense grid, or at least as far as this box extends. This is a dense grid that is not doing any memory saving things. It's just storing the distance at each voxel, to the best of its ability everywhere all the time. So if you switch back and forth between these two, you can see the colors right around where it changes over are the same. It's only the deeper ones and the farther out ones that are changing out here. In fact, you can just increase this band. And the more we increase it, the closer it'll get to looking like the other one. Now there won't be as much of a difference between the two. Of course, the more we do this, the more memory we're taking up, and then the less of a point there was of using this VDB approach. So, just so you know, the point is, we're going to see things like this a lot. The surface of the liquid in this lesson is often represented as a sign distance function. Other operations we're going to do, such as when we create our environment or when we want to shape our source, and a lot of things are going to involve sign distance functions. So I want to just make sure that you know what that is. It is a volume that stores, it essentially represents geometry by storing how far we are to the surface of that geometry in every voxel. And as usual, the coarser it is, the worse representation we're going to get. And the higher res it is, the better representation we're going to get of the thing, but at a cost of memory and, as you can see here, calculation time. So that is it.